Hello students, welcome to this module, which is part 2 in the series on Rayleigh-Taylor instability. Here we are going to do a more rigorous mathematical analysis using the normal mode stability formulation. Okay. Okay, the configuration that we are interested in is as follows. You have an unperturbed interface, which I show using dotted lines. Okay, and you have a perturbed interface, which I show like this. Okay, and you have a coordinate system xy, Cartesian coordinate system. This is x and this is y. Okay, and this is fluid 1 and this is fluid 2, and gravity is acting vertically downwards. Okay, and the interfacial deflection from the flat unperturbed interfacial location is denoted as eta. Okay, now as in any stability analysis, first we have to write down what are the base state variables and quantities. So the base state is a stationary case of two fluids being static, so the base state quantities are denoted by an over bar. So uj is 0, where j is 1 and 2, denoting the two fluids. Eta bar is 0. In the base state, the interface coincides with the vertical displacement of the interface is 0, so it coincides with the y-axis, y equal to 0. Okay, it coincides with the x-axis, and the pressure is hydrostatic. Okay, so Pj of y minus P naught is minus rho j gy. Okay, so what this means is that when y is positive, as you go above in this direction, the pressure should decrease, whereas when y is negative, as you go down, the pressure should increase because gravity is acting in this direction. Okay, so this negative sign accounts for that, and j is of course 1 and 2. And we're going to assume perturbations to this base state, and we're going to examine whether these perturbations are going to grow or decay. Okay, so the perturbation velocity is given by the base state velocity uj bar plus uj prime. Okay, the perturbation, the total, sorry, this is the total, this is the base state, and this is these are the perturbations. Okay, now Pj again is similar to the velocities plus Pj prime. Eta is eta bar plus eta prime. Of course, we know that uj bar is 0 and eta bar is 0, whereas Pj bar is given by this expression for the hydrostatic variation. It is customary to assume the flow of the flow due to the perturbations to be irrotational. Irrotational means that there is no vorticity in the two fluids in the perturbation flow, and therefore you can write the velocity field in both the fluids as the gradient of a potential, where phi j is prime is the perturbation velocity potential. Okay, this is basically you are thinking of the flow to be potential flow, because we have assumed inviscid fluids, and inviscid plus irrotational flows are potential flows in fluid mechanics. Okay, so this is called the velocity potential. Now I'm going to assume only two-dimensional perturbations. What do I mean by this? I'm not going to worry about, suppose I have an interface. There is also the direction into the screen. Okay, I'm not going to worry about variations in that direction. So I'm going to assume that this is very large in extent that it doesn't matter whether you consider it or not. So you're going to only worry about flow in the xy plane. There is no z variation along this direction. Okay, now del dot v is 0 and v is del phi combined to give del squared phi is 0, and therefore you'll have partial squared phi j partial x squared plus partial squared phi j by partial y squared is 0, and j takes the labels for both the fluids. Now at the this is the unperturbed interface. Okay, let me draw it properly. Let's say this is the unperturbed interface and you have a perturbed interface due to the fluctuations that are present in the in any system, right? And at this interface you have to apply velocity and stress continuity conditions. Now since we are looking at inviscid fluid, okay, we are making the inviscid flow approximation. This means that we cannot apply the tangential velocity continuity and cannot apply the tangential stress continuity. Because when you go from the viscous to the inviscid limit, you lose the highest derivatives in the Navier-Stokes equation, and that means that you cannot satisfy all the boundary conditions. So usually in the inviscid flow analysis you forego the tangential velocity and tangential stress conditions, and the total stress in the fluid is just the pressure. There is no viscous stress because the fluid is inviscid. Now therefore the velocity and pressure continuity will amount to normal velocity continuity and normal stress continuity. And in the normal stress you consider only the pressure because there are no viscous normal stresses because the fluid is assumed to be inviscid. Okay, the normal stress continuity is the pressure equality at the perturbed interface, but the pressure itself in both the fluids is given by the unsteady Bernoulli equation, which is the unsteady generalization of the usual steady Bernoulli equation. Let me write this first. Okay, okay. The usual Bernoulli equation is P plus half rho u squared plus h rho g is some constant, and it is quite similar to that. This is the unsteady term and this is the kinetic energy head, because del phi is v is del phi. We just saw this thing, right? So this is the kinetic energy term, this is the pressure head, and this is the gravity term. So this is the generalization of the usual Bernoulli equation to unsteady flows. Okay, now let's imagine how to find these constants Cj which are there in the unsteady Bernoulli equation, and in order to do that, first let's assume that apply the Bernoulli equation to the base state, the above Bernoulli equation in the base state configuration. What will happen? we have P bar j, there are no perturbations now, plus rho j gy is Cj. Now we have to substitute from the base state. We know that Pj of y is P naught minus rho j gy. When you substitute that, you will get P naught minus rho j gy, that is from here, plus rho j gy, that is from here, is Cj, but these two terms will cancel, implying that Cj is simply P naught, where j is both 1 and 2. Okay, so it doesn't the constants that appear in the Bernoulli equation are simply the value of the pressure at the interface, which is an arbitrary number for incompressible flow. Okay, and now we are going to subtract this from the total Bernoulli equation, which will give us the Bernoulli equation for the perturbations. So rho j t plus half rho j prime is 0. Okay, so this is what we will get in the perturbations after substituting for the base state quantities and removing the base state quantities. All you will get for the perturbations of Pj prime is 0. Okay, the boundary conditions for the velocity potential are that Phi1 prime should go to 0 as y goes to minus infinity, and Phi2 prime should go to 0 as y goes to plus infinity, because the fluctuations of in velocities and velocity potentials should decay as you go very far away from the flat interface. Okay, now let's move to the kinematic condition, which will tell us about how the interface is going to evolve as a function of time due to the adjacent fluid motion. The kinematic condition simply says that if h is equal to y minus eta of xt is 0 is the equation of the interface. Okay, then the kinematic condition simply states that dh dt is 0. Okay, now which simply says that partial h partial t plus w dot del h is 0, where w is basically the velocity of a point on the interface. Okay, now if I were to take this to the other side, is minus partial h partial t. Now if I do, I'll get okay, but we know that this is nothing but the unit vector n, so we can write w dot n, this implies is minus 1 over dt. Okay, but h of x y t is nothing but y minus eta of xt, so partial h partial t will be minus partial eta partial t, but there is another minus sign, so what you will get is w dot n is 1 over mod del h. Okay, right, so now what is del h, what is grad h? It's nothing but partial h by partial x ex ey, and this is nothing but minus partial eta partial x ex plus ey, because partial by partial y is just 1, and if you do this, then del h dot del h to the power half is mod del h will give you 1 plus partial eta by partial x squared to the half. Okay, and therefore w dot n from here is nothing but, you have 1 over delta h, so you write partial eta by partial t, okay, divided by okay. Now this is the exact equation. Now the velocity continuity, the normal velocity continuity implies that uj dotted with n is w dotted with n at y is equal to, and j is 1 and 2. Okay, these are the two values that the two fluids can take. Okay, now you have to think of what is n. Okay, n is nothing but del h by mod del h, so n is nothing but divided by half. So we do now one thing that you can imagine is that in a linear stability analysis, in the denominator 1 plus something squared to the power half. So in a linear stability analysis, this square term can be neglected, so n can be approximated in linear stability. N can be approximated as minus partial eta partial x ex plus ey, because the denominator is just 1 to linear within the linear approximation, and therefore what you have to do is, in order to do this, you will say that uj is partial phi j by partial x ex. Okay, now all you have to do is, these are all perturbations. Okay, so all you have to do is substitute this out here and equate it to w dot n, which is what is w dot n again? It's approximately, this is unity within the linear analysis. So okay, when you do this, what you will get eventually is that partial phi 1 prime by partial x minus partial eta by partial x plus partial phi 1 by partial y is partial eta by partial t, and similarly partial phi 2 in eta prime this is all to be applied at this location, the perturbed interfacial location. We'll come to this in a moment. Now in the linear stability analysis, these are all non-linear. These are non-linear, so these are neglected. So all you are left with is rather simple expressions for the velocity continuity in this form. Okay, so all we have is partial phi 1 prime is partial eta prime by partial t okay. So now let's go to the stress continuity conditions. As I told you, in stress continuity you don't have viscous effects. Okay, so what you'll have is n dot t dot n 2, remember this is 1, this is 2, this is n, right, minus n dot t dot n 1 is equal to gamma del dot n. But note that in an inviscid fluid, in an inviscid fluid. T2 is minus P2I and T1 is minus P1I, okay, where I is the identity tensor. Therefore, when I substitute this, all I will get is P1 prime, sorry, now this is the total stress. This has both the base state plus perturbations. So P1 minus P2 is gamma times del dot n, okay, but n is nothing but Ey minus partial eta by partial x Ex by half. Now you can neglect this nonlinear term and just do del dot n very easily, or you can include this. Either way the answer apparently doesn't change. So del dot n is simply, what you'll get is minus partial squared eta by partial x squared, okay, to linear order, because we are doing linear stability analysis, so we are going to retain terms only up to this order, okay. So okay, now right, so now P1 minus P2 therefore is, from this expression here, is minus gamma partial squared eta by partial x squared. Now note that this is the flat interface, this is the curved interface, this is 1, this is 2, this is eta. When eta is a maximum, the second derivative of eta is negative, negative of negative is positive. So when the interface is bent like this, the pressure here P1 is more than the pressure here P2, and that is in agreement with what surface tension does. Whenever there is a curving in on the concave side, the pressure is more than the convex side. This is the basic idea of surface tension. So that agrees with what we just derived as well, right? So now therefore what we have done so far is that we have set up the problem, we have linearized the boundary conditions, we have these two velocity boundary conditions, okay, sorry about this, right, and we have the we have both the kinematic condition and the continuity of velocity conditions yield this, and then we have the pressure continuity condition which yields this, okay. Now what we have to do next is to finally go to solve the differential equations, the potential flow equations. So what we are going to use is the normal mode expansion for the perturbation. So what we are going to do is, we'll say phi j prime of x y t is nothing but phi cap j y times e to the I k x times e to the minus I omega t, okay. So here k is a real wave number and omega is a complex frequency, okay, and if omega is real, then there is only oscillation. If omega is complex, the imaginary part will tell us whether things are stable or unstable. And these are the eigenfunctions which are unknown a priori, but this has to be calculated alongside as we solve the problem, okay. So now what we have is partial del squared phi j prime is 0, and if I do the Fourier decomposition of this, first let me write this down. if I substitute this expression here, in the x derivative we will differentiate only this. If you differentiate once, I will get ik times e to the ikx. If I differentiate it twice, I will get minus k squared, because ik times ik is I squared k squared. I squared is minus 1. So this will give rise to d squared by dy squared minus k squared and j is 1 2. Okay, now this is the equation that we need to solve, and the unsteady Bernoulli equation for the pressure stated that rho j partial phi j prime partial t plus half rho j del phi j dot plus pj prime is 0. This is non-linear, so we neglect it in a linear analysis because here there is no velocity in the base state. So if I Fourier decompose this, that is if I substitute the normal mode expansion, what I'll get is minus omega rho j phi j cap plus is 0. Okay, these are the boundary conditions. Sorry, this is how the pressure is related to the velocity potential. Okay, and the pressure also comes via the interface condition, which we just this is the linearized interface. This is the interfacial condition, wherein the surface tension term is kept up to linear order. We'll discuss how we handle that in a moment. Okay, now right, so the boundary conditions are phi 1 cap of y goes to 0 as y goes to minus infinity, phi cap of y goes to 0 plus infinity. Okay, now and further you have the interface conditions which we discussed here. So this has to be Fourier decomposed as well. When I do that, what I will get is very simple. Partial phi 1 y is minus I omega eta hat. You need not have partials because you can simply have ordinary derivatives, because the hat quantities are functions only of y. I'm sorry. These are all. Now in principle this has to be applied at y is equal to eta of xt, the perturbed interface, because that's where things are continuous. Okay, now a very important feature about interfacial instabilities is that because the perturbed location y is equal to eta of xt is unknown, and because in a linear stability analysis this is a small quantity, you can Taylor expand the quantities at the unperturbed unknown at the perturbed unknown location to the unperturbed known location, thereby getting explicitly factors of eta. But the advantage is that you will be able to apply the boundary condition at y is equal to 0, which is a known boundary. Okay, this is a very standard technique that is used in interfacial instabilities. So I will explain this in the next module in a lot more detail, how to do the linearization of the interfacial conditions. Right, I will stop here at this point and we will continue in the next module. Thank you.